everyone. I know what you're thinking. Great intro. Thank you. I really appreciate it. Today's topic is integration. Before we get to integration, however, I want to go over some things with derivatives because integration is actually the inverse of derivatives. So again, this is integration on a pre-calculus level. And so we did derivatives on the pre-calculus level. So it was very basic derivatives, kind of just twinkling our toes in the pool of derivatives. We haven't found a full landscape yet, but we basically did the following things. We did something called the power rule. And the power rule basically states if I take the derivative of x to the power of n, I get n times x to the power of n minus 1. So if I take a derivative of a polynomial function, I'm going to move its exponent down, and the new exponent is going to be 1 power less. And just if there was a coefficient in front of this polynomial function, let's say it was k times x to the n, it would just be this same result, multiplied by k. So it would be kn x to the power of n minus 1. Meaning basically we're multiplying the exponent by k, by the coefficient, and we're still subtracting 1 from the exponent of x. Those are the basic derivative rules that we looked at in pre-cal. We also did the quotient rule, but that's not going to be germane to what we're doing today. So these are the two things we want to remember. So I just want to do a couple examples to refreshen ourselves with taking derivatives of polynomials. So these are just some basic examples just to get us warmed up. I consider this a warm-up lap in the derivative race. So let's say some function f of x is 13x to the 4th minus 2x cubed plus 8x plus 9. And we're going to find f prime of x. So we're going to find f prime of x, better known as the derivative. And again, I'm going to use that power rule. So when I take these derivatives, I'm going to multiply this exponent by this coefficient. 4 times 13 is 52. And then I'm going to subtract 1 from the exponent. Similarly here, 3 times 2 is 6. And then I'm going to subtract 1 from the exponent. Same thing here, the exponent is 1. So 1 times 8 is 8. And then I'm going to subtract 1 from the exponent. This exponent is 1. If I subtract 1 from it, I get 0. Anything to the power of 0 is 1. X to the power of 0 is 1. So 8 times 1 is just 8. So there's no need to write the 8. Another rule we talked about, which is really just something with the power rule, if I take the derivative of a number times x, I just get that number. Same deal here. I'm still really using the power rule. This is 9 times x to the power of 0. Well, 0 times 9 is 0, and 0 times whatever's left is going to be 0. So the 9 is going to drop off. So in general, the derivative of a constant is 0, but it still really follows the laws of the power rule. So this is the derivative here. So what about integration? Now, just as we just kind of twinkled our toe in the pool of differentiation or finding derivatives, we're also going to twinkle our toe in the massive pool. I'm talking about massive, the massive pool of integration. We're going to do something called finding an indefinite integral, but I'm going to title this integration. What I'm finding, they're also called antiderivatives because they're the inverse of derivatives. So a few synonymous terms: indefinite integral, integral, antiderivatives, that's all the same. So here is an example. And we're going to do this intuitively. You're smart people, you can figure this out. So we're going to look at this intuitively. I claim if I define what an integral is, so the process is called integration. The result of the process is called an integral. So I claim if I can define what an integral or an antiderivative is, you can find it yourself based on what you know about derivatives. So here is an example. So I'll take the integral of 7x to the 6 dx. I'm going to find that answer. All right. Now I want to point a few things out. This strange looking symbol here is called an integral sign. It kind of looks like an S, because really how this is developed, and it's not something I cover in pre-cal, I cover it in calculus. So if you're lucky enough to make it to calculus, you'll understand that this represents a sum. And so it's like a fancy looking S is what it really is. It actually represents a sum. But to explain that is a bit beyond the scope of pre-calculus, but it represents an S. Now, this guy here, I'm going to give you a Kool-Aid definition of this. So I'm going to give you a very elementary definition. This just tells you, for now, again, as we get deeper, you'll learn a little bit more. But for now, this just tells you the variable which you're integrating with respect to. So I'm integrating with respect to x. Now, a little later, this has some applications. Sometimes it's called an infinitesimal and different things. For us right now in pre-cal, we're just going to say this means you're integrating with respect to x. And I'm going to need that dx every time I integrate. So I need it. It's not something that I can put there and maybe not put there depending on how I feel. I need this every time. And again, if you're lucky enough to make it to calculus, you'll get a better understanding of what that represents. But for now, just say it represents the variable I'm integrated with respect to. All right. So this is what this problem is asking us to find. This is asking us which function can we take the derivative of and get 7x to the 6. Think about it for a second. It's asking which function can I take the derivative of and get 7x to the 6. Now, many of you already know the answer, correct? And you're thinking of the answer because you're smart kids. And a lot of you have thought of the answer. And I don't think you know all of the answers, however. But I know you're probably thinking of one. So I'm going to assume you're saying the answer is x to the 7th, correct? Now, if you think that's the only answer, you're flat out wrong, folks. Now, I want you for a second to think of another answer to this problem. I myself can think of an infinite number of answers to this problem. But I want you for a second to think of another answer to this problem. So x to the 7th is one answer. It is what we call an antiderivative. It's not the antiderivative because there's multiple. It's an antiderivative. Can you think of another? Now, some of you may have thought of some of you may have not. I'm going to help you out a little bit. I'm going to give you another answer to this problem. X to the 7th plus 4. If you take the derivative of this, you're going to get 7x to the 6. I can think of another one, x to the 7th minus 6, x to the 7th plus 1/2, x to the 7th minus pi, x to the 7th plus 2.28, etc. There is an infinite number of answers depending on this constant. This is why this is called an indefinite integral, because there's an indefinite number of answers you can have here based upon a constant. So what we normally do in a business, because this answer can vary based on the value of the constant, is when we answer these, we put plus c. So the c represents any constant. So the real answer to the problem is x to the 7th plus any constant. It could be any number of constants. Okay, so now that you know that little technicality, I can put several more examples up, and you'll probably know the answer instantly. For instance, if I was bold enough, and I am, to integrate 10x to the 9 dx, I think you know the answer, correct? And you're right. So the answer is x to the 10th plus C. And so right now you're probably thinking, man, this is pretty simple. And you're right. However, all problems will not seem as simple as the problems you've seen thus far. So let's increase the complexity just a tad, shall we? Let's put a little salt on this chili. All right. Let's integrate 3x to the 11th dx. Okay, smarty pants. I want you to think about this answer. 3x to the 11th. Let me give you a moment to think. So we're trying to see which function can we take the derivative of and get 3x to the 11th. Okay. Some of you may have figured it out. Some may still be wondering. Let's end all the wonder, and the answer should be 1 over 4 x to the 12th plus c. So you can check it by doing the derivative. If I take the derivative of this function, I have 12 times 1 over 4. 12 times 1 over 4 is 3. Subtract 1 from 12, I get 11. Okay, so I up the ante a little, yes? But wait, it gets better. Watch this. I just put a little pepper in the chili. I'm about to throw a jalapeno in this bowl. Watch this. Okay, let's go the integral of 7x to the 19th dx. 7x to the 19th dx. Give you a moment to think about that guy. This is a smart kid question. All right? Think. We're doing this analytically and intuitively. Just think, let the brain work. Some of you probably have an answer. I would like to share the answer with you. The answer is 7 over 20 x to the 20th plus c. Now look at it very carefully. Again, if I was to take this derivative, I would multiply 20 times 7 over 20. The 20s would cancel. I would be left with 7. I subtract 1 from 20. I get 19. It's getting easier, yes? Okay, let's try another one. Let's integrate 5x to the 6 dx. I'm going to give you a moment to think about this one. 5x to the 6 dx. Alright, you should have came up with it by now. And the answer should be 5 over 7 x to the 7th plus c. Again, you can check it by taking the derivative and you'll see the answer works. Okay, some of you are getting the groove of this. Now, some of you may not be getting these answers. And if you're not getting these answers, I have a formula you can use. So we've been doing this more intuitively, but there actually is a formula that describes this phenomenon. Again, this operation, integration, is the inverse of differentiation or taking a derivative. And if you recall, this is our power rule for derivatives. We have this power rule for derivatives where the derivative of x to the n is n times x to the power of n minus 1. Well, let's think about doing the opposite of what's occurring here. Now look very carefully, and I'm going to use this example as a way to set up my formula. So I'm about to deliver, right before your very eyes, the power rule for integration. So if I was to integrate x to the n dx, what would I get? Now, one thing you should notice about the problem and the answer is the relationship between the beginning exponent and the ending exponent. It went up 1, correct? When you take the derivative, the exponent goes down 1, right? Well, when you integrate, the derivative goes up 1. So notice it went from 6 to 7. So if I integrate x to the n, I'm going to get x to the power of n plus 1. I'm going to go up a power. Now what you may also notice, again, disregard the 5. The 5 is just a coefficient. So it doesn't really do anything. But let's look at what we're dividing by. We're also dividing by 7, right? So this new exponent that we get, this n plus 1, we always divide by it as well. So the integral of x to the n is x to the n plus 1 divided by n plus 1. That's the power rule of integration. And just to, you know, if there was some number in front of x, so if I'm integrating k x to the n, then it's just k times x to the n plus 1 divided by n plus 1. So, you know, plus, of course, you know, plus some constant. I don't write plus c when I'm writing these generic formulas, but in a regular problem, you know there's going to be a plus c. If you look at every problem we did thus far, it all applies to this rule. So, with this newfound information, let's do some more examples. All right, so let's integrate 13x to the 10th dx. So we're going to integrate 13x to the 10th dx. Now, believe it or not, a lot of people think integrating is a very difficult process, integrating polynomial functions. And I always say integrating is as easy as adding 1, because the only math I'm doing in this whole process is here. That's it. All I'm doing is adding 1 to the exponent. That's the only math I'm doing. Despite how difficult it may seem, all I'm doing is adding 1. So here's the scope of the mathematics that I have to do. Well, of course, sometimes maybe I need to simplify this fraction. Okay, I'll give you that. But we simplify fractions like 3rd or 4th grade, so that's simplistic as well. So what I'm doing is adding 1, and maybe I have to simplify some fraction. That's the basis of it. So look, when I do this problem, my main operation is to add 1 to 10. It's x to the 11th. So that's 13x to the 11th divided by, yes, you guessed it, 11 plus some constant. Take the derivative. Check it, non-believers. If you take the derivative, these 11s will cancel. 11 times 13 over 11, the 11s cancel. You're left with 13. Subtract 1 from 11, you get 10. It's as easy as adding 1. It's as easy as adding 1. Let's do another example, shall we? So say we integrate 2/3 x to the power of 5 dx. The beauty of mathematics, we don't care if the number is positive or negative, fraction or integer, rational or irrational, the same rules always apply. So now I have a fraction or a rational coefficient. Big deal. I'm still going to add 1 to this guy, and that's going to be my new exponent, and I'm going to divide by it. So again, the scope of my mathematics is adding 1 to 5. 5 plus 1 is 6. So this is 2/3 x to the 6 over 6. So I'll write x to the 6 over 6 like that. There is some plus c. So in this problem, I have to simplify a fraction a little bit. Big deal. We can simplify fractions. That doesn't kill us. So I need to simplify this fraction. If you want, that's 2 over 18, which is 1 over 9. 1 over 9, excuse me. How I like to simplify something like this. Again, I just like to divide this 2 into the 6 if it can go into it. and that'll be 3, and 3 times 3 is 9. Of course, when we're simplifying, we're only dealing with these regular numbers. We can't touch the exponent of x. We can't touch the exponent. It's an MC Hammer. Can't touch this. So you can't mess with this, but these regular numbers, they're all fair game. So this is, you can write it as either 1 over 9 x to the 6 or x to the 6 over 9, however you prefer. I guess I write it as 1 over 9 x to the 6 plus some constant. And again, if you were to take this derivative, so let's check. If I was to take this derivative, I'll multiply 6 times 1 over 9. 6 times 1 over 9 is 6 over 9. 6 over 9 simplifies to 2/3. And I'll subtract 1 from this exponent, and I'll get 5. And I haven't mentioned, of course, and I take the derivative of this constant. Derivative of a constant is 0, so that's why that's the only thing you see there. All right, let's try another one, shall we? And this is what I consider a good time. So let's integrate if we can. Let's integrate 3 over 10 x to the 19 dx. Let me give you a moment to try that problem. Try that problem if you will. If you need to pause the video. Give yourself time to solve this problem before I come back. Don't let me have all the fun. You need to join in the party as well. Alright, that should have been enough time. If it wasn't enough time, just pause the video, finish the work, and then start the video. So our answer should have been, again, my process, folks, all I'm doing is adding 1. I promise that's all I'm doing. And I know that 19 plus 1 is 20. So guess what? This is 3 over 10 x to the power of 20 divided by 20 plus some constant. And for now, just simplify. What you should notice is that 3 neither divides evenly into 10 or into 20, so this can't be simplified. And so this will be 3 over 200. 3 over 200. Again, I'm multiplying 10 times 20, x to the 20th plus c. I could have also wrote 3x to the 20th over 200. Same thing, of course, just different ways of writing it. Okay, my pre-cal students, that concludes this lesson on integration. What I'm going to do is I'm going to put an assignment on integration. Again, this is advanced work for those trying to get ahead, so this is an optional assignment. But for those that choose to do it, I am going to apply some extra credit. That's not something I normally do, extra credit, but in these conditions, for those going out their way to learn these advanced topics that I'm going to begin to drop, there will be some extra credit. So look for an assignment on indefinite integrals and have fun and do that work. It's been a pleasure. Until next time, we're out.